Hey guys, welcome to another episode of the Algorithmic Illustrator. In this particular video, we're going to go over finding the LCA of a binary tree. LC here stands for least common ancestor. The important part of this problem is that we want the least common ancestor of a binary tree, not a binary search tree. If our problem was binary search tree, the solution would be a lot simpler and the approach would be a lot simpler. But in this case, it's a binary tree, so the approach is slightly going to be different. So as you can imagine, the problem statement is this, is what I just said right now. Given a binary tree, find the LCA of two given nodes in the given tree. Okay. So the for those of you who don't know what LCA means, it's the least common ancestor. So the keyword there is ancestor. So as an example here, given this particular tree, 5 is the ancestor of 6, but 5 is also the ancestor of 2, 7, 4. So if we were to find the least common ancestor, it would of say like 6 and 4, it would be 5. Right, so that would be the least common ancestor of this. 3 would also be the ancestor of 6 and 4, but we want the least common ancestor. So that is what we mean by LCA, or least common ancestor. So here's a few examples. So least common ancestor 6 and 4 would be 5. The least common ancestor of 5 and 7 would be 5 itself. So it could also be the node itself, right? So there's multiple approaches of solving this particular problem. So one very simple approach goes something like this. Okay, so if we can write a generic function that can capture the path from the root to the particular node that we're looking for, we can essentially generate two paths. And then we can just compare those two paths and figure out which one is the least common ancestor. Okay, that might sound complicated, but it's actually really easy. So as an example here, if I were to find the least common ancestor of 6 and 4, what I would do is I would get the path from the root, which is in this case 3 to 6, right? Which would be something like 3, 5, 3, okay? 3, 5, 6, sorry, 3, 5, 6. And I would do the same thing if I were to find, for least common ancestor of 4, I would get the path from the root, which is 3, all the way until 4, 3, 5, 2, 4, right? Which should be 3, 5, 2, 4, okay? So once I have this information, what I can basically do is I can traverse through this array, and the point at which the values diverge, which are not the same basically, the previous value before that is my LCA, is the least common ancestor, okay? That's the basic idea of it, okay? So if you were to write some sort of generic function which can take the root, right? It can take in the node that you're looking for, right? And basically basically output, give you a particular path, right? You can accomplish that task, okay? So let's see how we can do that, okay? So I'll call this find path, right? And this might take in a root, the node that you're looking for, and the path, which is like probably a list or array or whatever, right? Let me use a pen here instead. So this is the idea. So for instance, if I want to find the path from 3 to 6, I would pass in the root node, which is 3, node, which is 6, right? And the path would be like a temporary array, right? This would be a temporary array, okay? So how can I accomplish this? Okay, so what can I put in the code here, okay? So you want to think about the tree structure in general, right? So in general, what you want to do is, the tree itself, right? It has a root, it has a left subchild, and it has a right subchild. And these themselves can be, root and left subchild, right subchild, and so forth. So it's a recursive structure, right? So let's start with the base case. So if the root is none, right? So if root, is none, right? Is null, right? Basically, then we return false, right? And the way we can think about this function is that we want this function to return a Boolean, okay? The reason why we want to return a Boolean is that, say we're at 5, right? You want to know if somewhere along its right subtree, for instance, the value 7 occurs, okay? And you can think of it in terms of Boolean, right? Because you can recursively compute the left subtree, right? You can recursively compute the left subtree, you can recursively compute the right subtree. And if you do see that 7 occurs later on, right, the recursive calls return a Boolean value saying it's true or false, saying that a particular value occurs later in the series, then you can start appending that and actually evaluating start appending those values to the given path. If not, you will have to pop the given element out of the given array, and you have to backtrack, right? That's the essential idea of it. Okay, so if that sounds complicated, it's not that bad. Let me show it to you how it's done. So if the root is none, then you return false. Okay, simple, right? Then what can we do, right? So if not, what we'll do is we'll add our given node, right, root to our given path, right? Okay, and we do some bunch of searches here, right? So we'll add those temporary values here. So say we're searching for 7, right? So we want the path from 3 to 7. We'll start with 3, we add it. We'll start with 5, we'll add it, and we'll do some searching on the left subtree and right subtree. And if we don't find it, we'll pop it off. We'll pop that element off, right? So we append it, and we have some search logic that goes here, right? And if not, we pop it off. So we take away the last inserted element, right? So we pop it off and we return false, right? Because it was essentially not found, right? The given element was not found, right? Because we're backtracking, okay? So search logic goes here, okay? So what does the search logic look like? Okay, so the search logic is pretty straightforward, right? So if you're at a given node here in the tree, and if the particular value of that node is equal to the root, right, that you're passing in, then you have essentially computed you've essentially found your given node, right? So instead of node here, I'll just call this target node or target, and root can be in general root, or as you're traversing down the tree, it can be in the node, right? So if root is equal to target, right? Again, it depends on the problem statement, but you can compare the references of the root themselves or the values depending on the problem statement, what it says, okay? In this Leetcode example here, they actually want you to compare the actual values. Basically, both of these are tree nodes structure, right? You don't do root.value equals target.value for this particular problem from Leetcode. They want you to compare the references and so forth. So if root is equal to target, right, then what you can do is you can return true, right? Because you've essentially found your given target, right? Else what we need to do is we need to check its left subtree, and if the given element exists within the left subtree or the right subtree, okay? So we also say something like if if left is not none, so if not, or if the left exists, right? So if root dot left exists, right, and the value occurs within the left subtree, so that's the recursive call here, and find path, right, root dot left, right, or a target, right, in path, right, and root dot right, same logic with the right subtree, and find path. So all we're saying here is that if we don't find the particular value in the particular target where we're at right now, it can either be in the left subtree or it can be in the right subtree, okay? And those are recursive calls. So you're saying that give me the Boolean value and see whether it can be found in the left subtree or the right subtree, which are these recursive calls here, which basically operate on the left and the right subtree, right? And so forth. So if root dot left and if the root dot left exists and it's not null, right, go ahead and recurse on the left subtree and see whether that will return true, right? And do the same thing with the right subtree, okay? This should actually be or, right? It could be either on the left subtree or the right subtree, right? If so, we return true, right? So as an example here, right? say we're at this particular value 5 here, and 5 has this subtree and this subtree, and say we're looking for the value 4. It could be either on the left subtree or the right subtree, right? So we go ahead and recursively say that return me the value. So this left subtree will return false, and this right subtree will return true because 4 is in it. Okay, so that's essentially what we're doing. We're saying go ahead and search on the left subtree, right subtree recursively, and if it's found on either one, return true. Okay, else we pop it off, pop the last element out. So if we're searching for a number like say 10 here, we go to compute, like we go into the left subtree here, we add it, we append it, right? And this will return false, so we pop it off, right? And we backtrack and so forth. So if not, we do that, okay? So this is general logic here for finding a path from a given particular node to the particular node from the root to the target, right? And if it's so basically after this is a helper function, right? So what you have to actually do is you have to find the path, right, from from the root to the target 1, right? And we have to find the path from the root to target 2, right? And get those particular arrays, right? And you have to essentially iterate over them, right? You have to iterate over them, and basically compare the point at which diverges the value before that is your actual LCA. Okay, so that is the first approach. The only disadvantage with this particular approach is that, first of all, the time complexity of this is of the height of the tree, right? Height of tree, and the space complexity is it uses extra space, so it would also be of height of tree. Okay. Okay, so this is the general idea. Okay, so let's think about this, right? So we are using extra space or extra arrays to actually do this particular problem. So let's see if we can do better on this particular problem. Okay. Hey guys, so previously we discussed an approach of finding the least common ancestor, but the problem with that approach is that it takes up extra space in the sense that we need to calculate and find the paths for each node for the target that we're looking for, and we have to do that twice, and so that result in a temporary array or list. Can we do better, or can we optimize this in some way? And the answer is yes. So how can we actually do this? And the key here is to let the recursion do all the heavy lifting for us. So we let the recursion basically compute the LCA for us, okay? And let's think about how we can do that, okay? And I apologize for any background noise, so sorry about that. So if you're going to let the recursion do all the heavy lifting for us, how can we basically find the LCA, right? And the key here is if we let, by definition, if we see that if the left subtree or the right subtree both return the found elements, right, in basically non-null references, then it is the least common ancestor. Okay, so we still can use the same idea as we did for finding the recursive finding LCA here with using basically the Boolean values here, right? But instead we can also return references themselves, basically the actual node references. And if both sides, the left subtree and the right subtree, both return non-null references, basically the addresses of the nodes themselves, then we know that we have found a least common ancestor. Okay, so in this example here, say you're at 5, right, and you're trying to compute the least common ancestor from 6 and 4. If the 6 returns 6 and this 4 is propagated and this 4 is returned on the right subtree, then both the left and subtree both return the found elements, right? So in that case, we can return true because we know that the given element that we're looking for is the least common ancestor. Else, what we have to do is we have to recurse. If the left subtree is present, we have to recurse on the left subtree, and the right subtree is present, we have to recurse on the right subtree. Okay, that is the logic, and it's very elegant. So but I mean, it can be tricky to initially come up with solutions. So here's the best way to think about trees, right? You have this some sort of node structure, and you have the left subtree and right subtree. Okay, so the idea is that for this particular problem, if the element is present both on the left subtree and the right subtree, right, and both of those return non-null references, then you know that the node that you're looking for is the least common ancestor. Okay. On the other hand, what happens is that if say this particular branch returns null reference saying that's not found, we have to recurse on the left subtree and further down this line, right? So that is the general idea of this particular approach. So let's think about the base cases, right? So find else CA, right? And this takes in a root, target 1, T1, and T2, okay? So what we can do is first we can set up the base case if, not root, right? This serves as a base case when it hits a leaf node, right? Return none, right? Because if we have hit the leaf node and it's still not equal to the value that we're looking for, we can essentially return none, right? So in the very end of the recursion, basically the very last, when we branch off and we for each of the leaf nodes we further call the recursive calls, we can return none, basically return null references, okay? Saying that we have not found a given target, okay? If not, what we actually have to do is we have to basically, before we look at the recursive case, right? If the root, is equal to the target 1 or the root is equal to the target 2, we can return the root, right? Because in this case, say, as I'm recursing down the line, right? Actually, let me explain this line after I have done the recursive case, right? So if not root return none, right? Else we have to recurse on the left subtree and recurse on the right subtree, right? So I'll do find LCA on the root dot left, right? Target 1, target 2. Find LCA root dot right, T1 and T2. So these are the left subtree LT, right subtree ST, right? And basically, if LT and ST return non-null references, right? If LT and ST return non-null references, then I know that the element that I'm looking at currently is the root, right? So return root, okay? So let me come back to the line, this one, right? So what this is saying here is that while I'm recursing on the left subtree, right subtree, if the root is equal to that element, the target I'm looking for, I return the root, okay? So as say I'm recursing here, and then somewhere here down the line, this element is found. So it returns that particular reference and then propagates that up, okay? And this is the result I'm capturing. So I'm saying that if the final result is found either on the left subtree or the right subtree, or actually in this case it would be and, right? If the result is found both on the left subtree and the right subtree, then return the root, because by definition, that is the LCA. Okay, so in that case, by definition, it is the LCA, okay? And if not, then what do I have to do? I have to recurse either on the left subtree or the right subtree and repeat this process, right? So if, left subtree exists, go ahead and recurse on that, right? Return LT, right? Else return the result of the right subtree, or right subtree RS, right? And that is the essential idea of it, okay? So just to reiterate, so in this methodology, we make the recursion do all the heavy lifting for us. And the way we make it do it is that we essentially have the recursive calls compute the LCA and return non-null references if they are found within the left or the right subtrees, okay? And if they both return non-null references, then we know by definition that the node that we're looking at is a LCA, okay? If not, then we have to either go ahead and look at the right subtree, traverse down the right subtree, or the left subtree, okay? while we're traversing at any point in the time, we see that the node that we're currently looking at is equal to one of the targets. Then we can return that the node that we're looking at and propagate it along the hierarchy of the nodes, okay, to the root, okay. And that's pretty much all there is to it. Again, remember this picture, and hopefully this logic makes sense. It's a recursive, definition, and if you remember this picture, it's kind of convenient to remember. It kind of helps you identify and define the recursive structure of the trees. So that's pretty much all there's to it. Let's go ahead and look at my submission on Leetcode. Hey guys, welcome back. So here we're on Leetcode for this particular problem of lowest common ancestor of a particular binary tree. Okay, and the solution is what I described, in my algorithm earlier. So here's the code just in case. Okay, so if root is none, then we return none, basically a null reference, saying that we have not found the particular thing that we're looking for. Sorry for the interruption. Someone rang the bell. But if the root is equal to p or root is equal to q, we'll come back to that later. But essentially, if not, we recurse on the left subtree and the right subtree. And if we do find that the left subtree and the right subtree return non-null references, then we can return the root or the current element that we're looking at. And along each recursive step, as we're traversing down a particular tree, if we do see that root equals one of the targets, we return the particular root, saying that this particular traversal is successful because we found the particular element that we're looking for. Else, if we're recursing down the tree and if we do not see that both the left and the right subtrees are giving you the non-null elements, then we either have to recurse on the left subtree if it's present, or recurse on the right subtree if it's present. If the right subtree was successful and it didn't return anything, right? So that's the general idea here. So let's submit and see what happens. Okay, you got accepted. Great. So see you guys in the next video. So this is the code in Python, and obviously take this code and code it in your favorite language. Okay, see you guys. Bye.